Our universe has planets that break every rule we know. They're not fiction. They're real worlds found by astronomers, and their existence is making us rewrite the story of how solar systems form. For a long time, scientists thought they had it figured out. They were guided by two main ideas, core accretion and disk instability, but the cosmos had other plans. So now we have a picture of the 30 most bizarre exoplanetary systems, systems that defy all the standard models, and we need to understand what they mean for our search for life. How can a planet orbit backwards? What does a world that could float in water tell us about cosmic diversity? The answers challenge our most basic assumptions about our place in the universe. What does it mean for a planet to be truly alien? For a long time, those two theories gave us a stable picture, a sense of order, planets forming in specific places, following clear rules which naturally led to systems like ours. It made our solar system seem standard, a common blueprint. That idea became the foundation. It shaped how we saw every new find. We expected to see more of the same out there. More calm, flat disks, rocky planets in close, gas giants farther out. It was a logical, clean story, but the universe prefers its own stories, more complicated ones. The first sign wasn't a crash, it was a wobble. Astronomers started sensing the pull of planets around other stars, and the information was odd, quietly odd. They found planets completing orbits in days, giant hot gas worlds right next to their suns where only rock should be. Orbits that were stretched out, not round. Each one was a misfit, a piece that didn't match the expected image. At first, the idea was to adjust the models. Maybe special events could explain it. A rare migration, a peculiar history, but then the number of planets grew from a few to thousands, and the strange ones weren't rare anymore, they were common. The old story of core accretion and disk instability wasn't wrong. It just wasn't the whole story. It was like learning the rules of one kind of music, then hearing a completely different kind. The models could handle the basic tune, but not the improvisation. All of that built a tension between what we thought and what we saw. It set up a real shift, making us ask not just how planets form, but what a system can even be. The first real break in the model was this one detection, 51 Pegasi b, found in 95. It was a gas giant, bigger than Jupiter, but its orbit was just 4 days, so close to its star. A year there is less than a week. The heat would be immense. And according to the rules, it shouldn't be there. A gas giant needs to form far out where it's cold, where material can slowly gather. Up close, that heat should have blown all the gas away before a planet could even form. But the data was clear. A giant where a giant couldn't be. The hot Jupiter, and the answer had to be migration. It must have formed out in the cold, following the old rules. Then it moved. It spiraled in through the disk of material all the way to that close orbit. And that idea changed everything, because that movement wouldn't have been quiet. A planet that big, moving inward, would be like a wrecking ball. Any smaller, rocky worlds in its path, planets like ours, would have been thrown out or destroyed. So the calm history of our own solar system, that might be the exception, not the rule. These hot Jupiters showed that a young system can tear itself apart. It can rewrite its own layout, and we're just starting to see how. Migration was one thing, but then they found something that didn't just puzzle them, it broke the rules entirely. A planet going backwards. You look at our solar system, the sun spins one way, all the planets orbit the same way. It's a single direction, everything moving together. That's what you expect. It comes from that original cloud spinning as it collapsed. So when they found planets HAT P7b, WASP 17b, their data said these worlds were in retrograde. Their orbit is flipped. They go the opposite direction their star spins. Imagine if Earth reversed its orbit. That's not a small detail, it's a violation. A deep one. How does a planet end up backwards? The formation disk gives everything a spin. To reverse an orbit, you need an outside force, a violent nudge. something powerful enough to flip a world's entire path. The leading idea is chaos, maybe a close encounter with another massive planet, a near miss that acted like a slingshot, turning the orbit inside out. Or maybe the star has a hidden companion, far out another star or a giant planet whose gravity over eons slowly twisted the whole inner system. This changes the story. It means a calm, orderly disk can produce a system that later tears itself apart. The planets we see now aren't necessarily where they formed, they're the survivors. The ones that didn't get ejected into the dark. It paints a picture of young solar systems as arenas, gravitational billiards, close calls and catastrophic encounters might have been common. Our own stable neighborhood, then, might be the exception. A quiet street in a universe full of cosmic traffic accidents. And if that's true, what does it mean for rocky worlds? For places that might host life? How many promising Earths were thrown from their orbits before they ever had a chance? The retrograde planet isn't just a curiosity. It's a fossil record, a permanent scar from a system's violent youth. It makes you question the idea of a stable, hospitable cosmos. A year can pass in less than a day. That's the reality for these ultra-short period planets. On one called Kepler 78b, a full orbit takes just 8.5 hours. From one sunrise to the next, you'd live an entire year. The planet is so close to its star that it's almost certainly a global ocean of lava. Surface temperatures soar past 2,000 degrees Celsius. It's a place of relentless, unimaginable heat. And its existence is a profound puzzle. Because according to the standard playbook, a rocky planet shouldn't be here. At this distance, the star's fierce radiation and gravity should have prevented solid material from clumping together in the first place. Even if it formed farther out and migrated inward, the extreme tidal forces would be catastrophic. They should have stretched and pulled the world apart. Or at the very least, stripped away any atmosphere long ago. Yet, there it is, a scorched, stubborn survivor. So how does it endure? One possibility is it's not a typical rocky world at all. Its composition might be exotic, denser, more metallic, forged in conditions we don't yet understand. Or maybe its history is one of pure catastrophe. It could be the remnant core of a much larger gas giant. Its outer layers violently ripped away by the star, leaving behind a dense, metallic heart to continue its blistering dance. These ultra-short period planets test the absolute limits of what we think a planet can be. They're not just hot. They're laboratories of extreme physics. They show us planetary formation can push materials to their breaking point, and sometimes beyond. And what does such a world tell us about the fate of planets that wander too close? It suggests the cosmos has a grim sense of finality, but also a strange capacity for creating survivors from the wreckage. Density is the real story of a world. It's the final number that tells you what a planet is, and some of those stories are impossibly light. The Puffy planets, like Kepler 51b, a gas giant with a density lower than water. If you could find an ocean big enough, the whole planet would float. It's not just a gas giant, it's a hot air balloon the size of Jupiter. This lightness, it defies what we know. The standard model for a gas giant has a dense core, rock and metal, wrapped in a massive atmosphere of hydrogen and helium. A planet like that should have weight. But these puffy worlds are like feathers, so what keeps them inflated? The main idea is immense internal heat, maybe from tidal forces, stretching the planet's interior as it orbits. Or from a unique atmospheric chemistry, one that traps stellar radiation like a blanket. That extra heat acts like a burner under a hot air balloon. It causes the outer layers of hydrogen to expand and expand and expand. They never settled into a dense, compact form. They stay inflated. This isn't just a curiosity of size. It's a challenge to planetary physics. It shows the category gas giant is too simple. There are compact, dense giants, and there are these swollen, ethereal ones. The rules for one don't apply to the other. Puffy planets make us ask what the true limits of an atmosphere are. How much can it expand before it just drifts away? And what does a fragile, inflated world tell us about the balance of forces that define a planet? It suggests some worlds aren't permanent monuments. They're temporary, brilliant clouds, held together by a precise recipe, heat and gravity, and maybe a precarious one. For a long time, a planet with two suns was just science fiction. Something from a movie. Then they found Kepler 16b, a real planet orbiting two stars, a real Tatooine that broke another idea. That planets need one star, a calm focus, to form and to survive. Here, the planet is in a constant tug of war. It orbits both stars, moving around their shared center of mass on a wide, stable path. But you have to think about where it was born. The disk of dust and gas around those two stars would have been shaped by two gravitational forces. It would have been turbulent, full of gaps and waves. A much more chaotic nursery than the smooth disk around a single star. By the standard models, building a planet there should have been nearly impossible. The competing pulls would have stirred everything up. It would have kept the building blocks from gently sticking together. They should have been flung away into the void, yet Kepler 16b is there, solid, stable. Its existence tells us planet formation is more robust than we thought, more inventive. It can happen in the most energetic cradles, the most complex ones, and that expands the map. Binary star systems are incredibly common in our galaxy. If planets can form in such dynamic places, then the number of possible worlds just got much bigger. It shows a kind of resilience in nature, a capacity to find order. To build a stable orbit even within the dance of two suns, it makes the cosmos feel more chaotic and more creative. If a planet can find peace between two stars, what other impossible places might hold life? The idea of a world made of diamond, it sounds like a fantasy, a treasure beyond imagination, but for a planet like 55 Cancri, it's a serious possibility. This is a super-Earth, several times more massive than our own. It orbits so close to its star that a year lasts only 18 hours. Its surface is likely an ocean of lava. But the real mystery is beneath that. Astronomers looking at its composition see hints of something else. It might not be built from the same things as Earth. Our world is oxygen-rich. Silicon and oxygen make the rock. Iron sinks to the core. But 55 Cancri could be dominated by carbon. So you have a world where graphite and diamond are the common minerals. Where mountains could be literal gemstones. How does a place like that exist? The standard model for how planets form starts with a cloud of gas and dust. A composition like its star. Our sun is oxygen-rich, so our planets are rocky. But if a star forms from a cloud that's unusually rich in carbon, then its planets would be built from that different recipe. 55 Cancri may have been born in a carbon-rich pocket of its disk, a place the old nebular models didn't predict. And under the crushing pressures inside this massive world, carbon wouldn't stay as graphite. It would crystallize, so vast layers of the planet's interior could literally turn to diamond. This isn't just about exotic geology. It reshapes how we see planetary ingredients. The cosmos isn't using one universal set of building blocks. It has many different kitchens, each with its own pantry. A carbon world means a history completely alien to our own. The volcanism would be different. The tectonics would be different. The very ground would be different. It means when we imagine an Earth-like planet, we might be thinking too small. The variety of solid worlds out there could include realms of crystal, of carbon fiber, of substances we haven't even named. The diamond world hypothesis, even unproven, opens a door. It shows the elements that make a planet are a matter of cosmic location and chance. And that chance can create worlds of staggering strangeness, almost mythical. A world that stops spinning, one side always day, the other always night. That's tidal locking. It happens to planets that orbit very close to their stars. And it creates a specific kind of world, the eyeball planet. Imagine a red dwarf star, dimmer and cooler than our sun. For a planet to be warm enough for liquid water, it has to orbit extremely close. So close that the star's gravity locks it. One hemisphere always faces the light. The other always faces the dark. So you have a world split in two. The day side is a permanent desert, scorched under a sun that never moves. The night side is a frozen wasteland, eternal darkness and absolute cold. But in between them, along that thin line of perpetual twilight, there's a possibility. Temperatures there might be just right. A sliver of the planet, a circular region, could have a liquid water ocean. From space, it might look like a pale blue iris, staring out from the dark, like a single eye. This isn't just a curious shape. It overturns what we think of as a habitable world. Our climate models, our ideas about weather, were built for a rotating planet, one with days and nights. They assumed a kind of symmetry. An eyeball planet is pure asymmetry. Its entire weather system would be one giant engine, trying to move heat from the day side to the night side. How would storms behave? Would hurricanes become permanent, raging along that twilight line? Could an atmosphere even survive? Or would it freeze out on the dark side and collapse? Then there's life. Could biology take hold in that narrow, temperate band? It would be a world without a day-night cycle, without the circadian rhythm that shaped all life on Earth. But red dwarfs are the most common stars in the galaxy. So these eyeball worlds might be the most common type of potentially habitable planet we find. Our search for a second Earth might not end with a planet that looks like home. It might end with a world that stares back, a permanent testament to the universe creating habitable conditions in the most extreme, lopsided places. The super puff takes that lightness and pushes it into the impossible. These worlds, like the ones around Kepler 51, they're the real enigmas. From a distance, they look like gas giants. They have that same swollen size, but their weight is different. Their mass is only a few times Earth's. You get a planet the size of Saturn that you could, in theory, lift. And it's not just a puffy atmosphere. It's a phantom, a huge, hazy shroud of hydrogen and helium with almost nothing at the center. No standard model of formation has a clear answer for how you build this. A rocky core that massive should have become a proper gas giant. It should have pulled in all the surrounding material, but here that process seems to have stalled. Or it failed. One idea is that these are exactly those stalled cores, worlds that formed late as the protoplanetary disk was already fading. They gathered a primary atmosphere, but the gas supply ran out before they could bulk up. They were left as overinflated embryos, never reaching adulthood. Another idea, more dramatic, is that we're catching them in the act of disintegration. Their immense, lightweight atmospheres could be boiling away under the intense radiation from their star. What we see isn't a stable planet. It's a temporary, brilliant halo. A world slowly evaporating, leaving behind just a dense, rocky remnant that makes them cosmic mayflies, here for a fleeting moment in astronomical time. We're witnessing a mysterious transitional phase, a snapshot of planetary evolution that's neither here nor there. They challenge the categories we use. Are they failed giants, or are they super-Earths wearing a costume a million times too big? Their existence suggests the line between a gas planet and a rocky one isn't a wall. It's a spectrum, and on that spectrum there are ghostly forms we're only starting to understand. Some systems don't feel like chaos at all. They feel like harmony. TRAPPIST-1, that's 7 Earth-sized planets all orbiting a small, cool star. Their orbits are stable, more than stable. They are mathematically perfect. The planets are locked in a resonant chain. Their orbital periods are precise ratios, small numbers. For every 2 orbits of the innermost planet, the next one out completes 3. And that pattern continues outward, a cascade of synchronized motion. It's cosmic clockwork, breathtaking precision. This resonance isn't an accident. It tells a story of a gentle birth. In the standard models, resonances can form when planets migrate inward together, through the disk. Their gravity nudges each other. They fall into step, like gears. But for a chain of 7 worlds to all be locked this way, their migration had to be incredibly smooth, incredibly slow. No violent encounters, no gravitational slingshots, nothing to throw the balance off. It's the opposite narrative of the hot Jupiters, the retrograde worlds. This system formed with a whisper, not a bang. It presents planetary formation as an act of orchestration, a peaceful, synchronized ballet, an architecture preserved for billions of years. It challenges the idea that all young systems must endure violent upheaval. Here, the chaos was kept at bay. The result is a haven, rhythmic stability. And that raises a question. If such serene systems exist, how many more are out there? Quiet, harmonious neighborhoods, planets moving in lockstep. Their orbits a silent music written in gravity. Some worlds don't settle into stable orbits. They're on a path toward complete dissolution. There's a planet KIC 12557548b that's actually evaporating. It's a rocky world, but it orbits so close to its star that the surface isn't just molten rock. It's turning directly into vapor. Stellar radiation and heat are blasting material off the planet, creating this vast, comet-like tail of dust and gas that streams out behind it. We don't see this world directly. Telescopes pick up its death throes as a flicker in the starlight. The dimming isn't clean and symmetrical. Like a solid planet passing by, it's variable, messy, the signature of a disintegrating atmosphere, a cloud of debris that changes shape and density every orbit. This is a planetary end state, captured in real time. Our models of how planets die used to talk in terms of billions of years, slow cooling, gradual atmospheric loss. But here, the process is violent, rapid, happening on a human timescale. We're witnessing the final act. It gives us a brutal, direct look at extreme atmospheric escape. The physics of a world being torn apart by its own sun. It makes you wonder how many other planets have followed this same fiery path. In the chaotic early days of a system, how many rocky bodies spiraled too close and met this fate? This disintegrating planet isn't just a curiosity. It's a time lapse, a demonstration of the ultimate cost for a world that wanders into the inferno. And it raises a deeper question about our own solar system's history. Did we have planets that once ventured too close to the sun, only to be reduced to dust and memory? A rogue planet, a world with no star, just drifting in permanent night. It's the ultimate break from the disk model, no dawn, no dusk. Only the cold light from distant galaxies and whatever warmth is left in its own core. These aren't failed stars. They're true planets, but they travel alone, and that forces a question. What makes a planet a planet? Our definition has always been about a star. An orbit, a solar address, a rogue planet has none of that. It's a citizen of nowhere, drifting through the void. Astronomers think there could be billions of them. A hidden, ghostly population, maybe outnumbering the stars themselves. So where do they come from? One path is from chaos, a young, violent solar system. Gravitational billiards. A planet, maybe a Jupiter-sized giant, gets too close to another. The interaction is like a catapult. It flings the planet out of the system. It breaks the star's hold and it's set free, on a one-way trip into the dark. That fits with the stories of retrograde orbits and hot Jupiters. It's the same turmoil, just a more final outcome. But there's a second possibility, more mysterious. Some of these rogue worlds might never have had a star. They could have formed directly, from the collapse of a small, isolated cloud of gas and dust. A miniature version of how stars are born. These would be planets that bypass the disk model entirely. They're not orphans, they were always alone. That idea rewrites the playbook. It suggests planet formation isn't exclusive to stellar nurseries. It can happen in the quiet, dark corners of a galaxy, where no star ever shone. The implications are staggering. If a world can form in isolation, then planets aren't just accessories to stars. They're a fundamental feature of the cosmos, as common in the darkness as in the light. And what would that world be like? The surface would be a frozen wasteland. But deep underground radioactive decay and the leftover heat from its formation could maintain a vast ocean. Liquid water, trapped under miles of ice, kept warm by the planet's own heart. In that absolute darkness, in that profound isolation, could there be chemistry? Could there even be life? It's a haunting thought, that the most lonely places might not be barren, they might be sanctuaries, hidden away from any sun's radiation. The rogue planet phenomenon doesn't just add a new type of world, it shatters the star-centric view. It tells us planets aren't bound to solar systems. They are their own sovereign entities, drifting through the eternal night. And in their silent journey, they carry the possibility that life, too, might find a way in the deepest, coldest dark. The strangest orbits are stretched. A world that goes from the edge of its star out into total cold and back. That's a highly eccentric path. Our solar system has these neat, circular loops. But many exoplanets follow these extreme ellipses. The distance doesn't shift a bit, it swings wildly. Take HD 80606b. At its closest, it roasts. Then it goes out, a long journey, farther out than Mars is from our Sun, into a deep freeze. Then it falls back toward the fire. This isn't a gentle change of seasons. It's a climatic roller coaster. Epic, brutal, that kind of path is a scar, a signature of violence. In the standard model, the disk is calm, orderly, planets settle into circles. Friction with the gas smooths the path. To get an orbit this stretched, you need a massive nudge, gravity. A close encounter with another giant planet. A near miss, it acts like a slingshot, yanking the world off its circular track onto this elongated path. This is gravitational scattering, the aftermath of a cosmic billiard shot. It means in that system's youth, the giant planets weren't keeping their distance, they were jostling, competing. Their gravitational shoving matches sent shockwaves through everything. Flung smaller worlds onto these extreme journeys, heating and freezing, so many eccentric planets, that paints a picture. Dynamical chaos as a common phase. A solar system's adolescence. Our own orderly neighborhood with its calm circles might be the rare one, the success story, the peaceful outcome. For every Trappist one with its harmony, there might be 10 systems where the giants stirred up chaos. Leaving behind these stretched orbits, tortured orbits, it makes you wonder about Earth-like worlds in a place like that. A rocky planet in a habitable zone. Could it survive? If part of its year it's flung into a deep freeze, only to be scorched on the return. That extreme eccentricity isn't just a curiosity. It's a fossil record, a system that failed to find peace, a permanent monument to the gravitational turmoil, the true crucible where most planetary systems are forged. To really see the chaos, you have to look at a star when it's young. O microscopii, it's a stellar toddler, maybe 23 million years old, and around it, astronomers are watching a construction site. A huge, dusty disk glowing in infrared. That's the protoplanetary disk, the nursery where planets form, and it's not calm. It's not that smooth, serene disk from the old models. Observations from Hubble especially have caught something. Fast-moving, wave-like structures. Giant arcs and ripples racing outward through all that dust. Like throwing a stone into a pond, but the waves are light years across, moving at tens of thousands of kilometers an hour. This is the disk in full rebellion. Turbulent, these aren't the gentle motions of dust grains sticking together. This is violence, and it means planet formation might not be a quiet, gradual thing. It might be a series of rapid collapses. Clumpy, the disk itself could be unstable, fragmenting under its own gravity, spawning planets directly, in a hurry. Or the star is the agitator. O microscopii is a flare star. It has sudden, massive outbursts, radiation, charged particles. Its magnetic field could be lashing the disk, whipping up these colossal waves, herding material into dense piles. Where planets could form almost overnight. This real-time view is a direct challenge. The old theories predicted a slow cook, a patient simmer. What we see at OMIC is a flash fry. A dynamic, stormy environment, where the rules seem rewritten by the moment. It gives us raw data. The old, smooth narrative is incomplete. Planet formation can be rapid, eruptive, deeply messy. Watching it happen is like getting the blueprint for a solar system, then seeing the builders ignore half the instructions, inventing new tools on the spot. It makes you ask if our own solar system's peaceful birth was a quiet exception, or if even we went through a phase like that. Spectacular, hidden turmoil. The raw ingredients for a planet are dust and gas, but the recipe is the mystery. Astronomers thought they had a key piece, a star's metallicity. That's the amount of elements heavier than hydrogen and helium. Iron, silicon, carbon, the stuff of rocks and metals. The logic was clean. A metal-rich star came from a metal-rich cloud. That same cloud forms the planet-building disk. More metals in the star meant more solid material in the disk. More material to build rocky cores. More cores meant a better chance for gas giants. It was a clear relationship. More metals, more planets, but the cosmos likes a paradox. They found stars with very low metallicity, ancient stars. By every calculation, they should be planet-poor. Yet they had gas giants. According to core accretion, building a rocky core for a Jupiter around a metal-poor star should be like building a sandcastle with a handful of grains. There isn't enough solid stuff. It should be nearly impossible, and yet there they are. Then you flip it. Some stars are incredibly metal-rich, cosmic treasure troves. And they have no detectable planets. Their disks were barren. This disconnect is profound. It says having the raw materials isn't enough. It's about the conditions. The disk's total mass matters. How long the disk lasts matters enormously. A metal-rich disk that's too thin or vanishes too quickly might never form planets. Conversely, a metal-poor disk that is exceptionally massive and long-lived might still forge a giant, through sheer persistence, or through alternate pathways like disk instability. The dynamical history matters too. The gravitational dances, the near misses we see in other systems that can erase planets or prevent their formation entirely. Regardless of the ingredients, so the metallicity rule isn't a law, it's a tendency, a suggestion. The real recipe is a complex cocktail, a dash of metals, a pour of disk mass, a measure of time, a sprinkle of dynamical luck, stirred together in the unique conditions around each newborn star. This mystery pulls back the curtain. It shows the true complexity. We can list the ingredients, but the art of the cook, the specific physics of each stellar nursery, that remains the deepest secret. There is this space between a star and a planet, a kind of in-between place, the brown dwarf. It's too massive to be a planet, but not massive enough to be a star. It can't sustain that core fusion, that burning of hydrogen. That's what makes a star, and it forms differently than a planet. It forms directly from a cloud like a star does. A collapsing gas cloud, so it's a failed star. It just cools down slowly over billions of years, but then there's the puzzle. We don't just find these objects out there alone. We find them orbiting stars, sun-like stars, and they are in close orbits. Orbits where you'd expect to find a planet like a gas giant. So what is it, really? Is it a planet that got too big? Or is it a star's sibling, a small twin that ended up drifting too close? That's the mystery, the brown dwarf boundary. It blurs all the lines. Take the system HD 33632 AB. It's an object several times Jupiter's mass. It orbits its star at about the same distance Saturn orbits our Sun. By where it is, it looks like a planet. But by its mass, it's in that brown dwarf zone. So how did it form? Did it form in the disk around the star, building up from dust and gas? A superplanet? Or did it form right alongside the star from the same cloud as a binary companion? And then its orbit just shrank over time to where it is now. We see one object, but its past could be either of two stories, two completely different histories. This isn't just about words, it's about how we define things. We want clean categories, star, planet, but nature doesn't work that way. Nature works in spectrums, in continuums. The processes that make stars and the processes that make planets, we thought they were separate. But now we see they can make the same thing. A massive object orbiting a star. It could be a planet built from a disk, bottom up, or it could be a stunted star born from a cloud. Top down, the result looks identical, so we have to shift our thinking. We can't just use mass or orbit to decide. We have to look for other signs, chemical signs. The atmosphere's makeup might tell us, did it form from the same stuff as the star or from a disk that was different? Often the clues aren't clear. It's ambiguous. These boundary objects mean a solar system's family tree isn't simple. It can be tangled, a main star, a brown dwarf that formed like a star, and then maybe planets orbiting each of them. It creates complex architectures, really complex ones. What this means for our search is that the universe isn't just stranger than we imagine. It's more indifferent. It doesn't care about our categories. In the cosmic workshop, the same materials can follow different rules and end up looking the same. A brown dwarf in a close orbit is a permanent question. A reminder that the most interesting finds are the ones that won't fit any label we make. This miniature solar system is a puzzle of pure density. You have the ultra-cool dwarf star TRAPPIST-1, and it has 7 Earth-sized planets. They all orbit closer than Mercury does to our Sun. The whole system could fit inside that one orbit with room to spare. It's a cosmic apartment complex. Planets are neighbors here, not distant cousins, and that density is the mystery, because a star like TRAPPIST-1 is tiny and dim. Its protoplanetary disk, the cloud of dust and gas where planets form, would have been small and light. There just wasn't a vast reservoir of raw material. Yet from that modest supply it forged not 1 but 7 rocky worlds. So the standard models ask how. How could so much solid material end up in that tight, inner zone? Where did it all come from? One possibility is an incredibly efficient process. Every speck of dust, every pebble in that inner disk was used. Nothing was wasted. The planets formed in place rapidly, from a disk that was unusually rich in rocks and metals right from the start. Another idea involves migration, but of a gentle, collective kind. Maybe these worlds formed farther out, in a more spacious part of the disk, and then migrated inward together in a synchronized chain, their gravity gently shepherding each other until they settled into that compact, resonant configuration we see today. This isn't the violent migration of a hot Jupiter. It's a coordinated movement, a planetary procession, and their prevalence is the real revelation. Red dwarfs, especially these ultra-cool ones, are the most numerous stars in the Milky Way. If most of them host these packed systems, then the most common planetary architecture in our galaxy is not a spacious solar system like ours. It is a tight, bustling neighborhood. Worlds huddled together for warmth around a faint red sun. This changes our perspective on what is normal. Our own solar system, with its vast gaps and solitary giants, might be the outlier. The exception, the galaxy may be filled with these intimate families, and that raises profound questions for life. In such a tight system, the gravitational interactions are constant. Tidal forces are immense. The worlds likely keep one face to their star, creating permanent day and night sides. Yet, within that constraint, several of these planets orbit in the star's habitable zone. The potential for liquid water exists, so we have to ask, could life emerge in a sky filled with neighboring worlds, where the other planets are not dots of light, but looming globes dominating the heavens? The ultra-cool dwarf system isn't just a scaled-down version of our home. It's a different blueprint for existence, one where planets are born in a crowd, and their fates are forever intertwined. Uranus and Neptune, they are ice giants. They formed far out, past the point where water freezes, that's the frost line, but then you look at other systems. You find a planet like GJ436b. It's Neptune-sized, but its orbit is incredibly close. A year there is just over 2 days. They call these hot Neptunes. And it's a contradiction, because at that distance from its star, the disk would have been too hot. Those light ices couldn't have condensed, so it couldn't have formed there. It had to form farther out, beyond its own frost line, and then it migrated inward. It spiraled in. That's the only answer, and that shows something. We knew about hot Jupiters, big planets that plowed inward, but a Neptune is smaller. Its gravity is weaker. Its migration would have been gentler, slower. And that gentleness leads to a question. What about its atmosphere? A normal ice giant has a thick hydrogen and helium envelope. But if you drag that world close to its star, that atmosphere gets blasted. Stellar radiation, stellar wind. Over billions of years, it could strip that light gas away. So what we might be seeing now isn't the original planet. It might be the stripped core. A dense world of rock and superheated water, with a thin, new atmosphere. Heavier elements boiled off from inside. That changes what an ice giant is. It becomes a phase, a temporary state. Migration isn't just for the most massive planets. It can happen to smaller worlds too, and it can change them completely. How many of these hot Neptunes started as icy giants and had their essence burned away? Their hot orbits are monuments to a journey that remade them. Our solar system is a flat disk, a spinning plate of worlds. That shape comes from its birth cloud, which is what the nebular hypothesis predicts. But you can have a tilted plate. Planets orbiting at a sharp angle, completely misaligned with their star's spin. That's not a thought experiment. It's a measured reality for many exoplanets, and it breaks another core assumption. Astronomers use the Rossiter-McLaughlin effect to see this. A planet transits, it blocks a tiny slice of the spinning star's light. They watch the subtle distortions in the star's spectral lines, and that lets them deduce the planet's path. Is it crossing along the star's equator or cutting across at a steep, polar angle? The data shows stunning misalignments. Some planets orbit perpendicular to their star's equator. Others even go backwards over the poles. A tilted orbit is a historical record. It's a record of violence. In a calm, isolated disk, everything settles into that shared plane. For a planet to be knocked into a high-inclination orbit, something massive had to give it a gravitational kick. Long after the disk was gone, one culprit is other giant planets in the system. A close gravitational encounter can act like a cosmic hip check, sending a world onto a tilted path. Another is a distant, unseen companion, a binary star or a massive planet far out. Its gravity slowly torques the entire inner system over millions of years, warping the orbits of everything within. Then there's the star itself. Stars can wobble. Their internal dynamics, the churning of plasma, or the pull of a massive planet, can cause the star's axis to slowly precess, like a spinning top winding down. From our perspective, it would look like the planet's orbits were tilting, but in reality, the entire reference frame, the star's equator, is shifting beneath them. So the calm, flat architecture of our solar system isn't a universal standard. For many worlds, the orderly disk of their birth was just a starting point. What followed was gravitational restructuring, a reshuffling of the cosmic deck that left planets on tilted, peculiar paths. It means the final configuration of a planetary system often isn't its original one. The peaceful order we see at home might come from a uniquely quiet childhood, while many other systems endured a turbulent adolescence, one that left permanent, angular scars. The dust tells a story. After a solar system forms, that disk of gas and raw material is supposed to clear out. What you're left with are the planets, and maybe a faint ring of leftover rubble and ice. A debris disk. It's the construction site after everyone's gone home, but some of these sites aren't quiet. They're not faint. They're brilliant, massive rings of dust. They glow in infrared light, and they orbit at distances where, in every model, a planet should be. The logic is simple. In a dense belt of material, gravity should cause it to clump. Planets should form, and if they do form, their gravity acts like a vacuum, sweeping their orbit clear of that fine dust. So a bright, dense disk in that specific zone is a paradox. It's either material that failed to become a planet, or it's material being actively managed by a planet we can't see. Take the star Fomalhaut. It has this stunning, sharp-edged debris ring. Like a cosmic bullseye. For years, astronomers thought they saw a planet there, Fomalhaut b, orbiting just inside the ring, maybe sculpting that inner edge. But further observations showed something stranger. That point of light wasn't a stable planet. It was likely an expanding cloud of dust from a recent, colossal collision between two unseen planetary bodies. So the bright ring isn't a quiet leftover. It's an active arena, a site of ongoing demolition that suggests a different story for planetary maturity. Maybe in many systems, the final stages aren't clean, they're chaotic, destructive. The building blocks, the planetesimals, they keep smashing together long after the main planets have formed. They constantly replenish the dust. The disk stays bright because it's fed by a hidden population of colliding asteroids and comets. Or the unseen architects are there. Planets could be shepherding the dust through resonant orbits. Their gravity confines the debris into narrow, bright bands without clearing it all away. Their influence is visible, but they themselves stay hidden in the glare of their star. This forces a question about efficiency. How much of a protoplanetary disk actually turns into planets? Our models assumed a reasonably efficient process, but these persistent, bright disks hint that maybe a huge fraction of the solid material never makes it into a major world. It stays as shattered fragments, a permanent asteroid belt, but on a monumental scale. It shows a gap between the neat, theoretical timeline and the messy, violent reality. A solar system might never truly be finished. Its history is written not just in the planets we see, but in the brilliant, dusty graveyards orbiting between them. A star can be torn from its home, not by choice, it's forced out. We've seen these hypervelocity stars moving across the galaxy at over 1 million miles an hour. They're like projectiles, flung from the galactic center by the supermassive black hole there, or ejected from dense star clusters by violent gravitational pulls. They're refugees on a one-way trip into the void, and their story raises a brutal question about the worlds they might have left behind, or the worlds they might have taken with them. When a star gets ejected like that, what happens to its planets? The gravitational bond is powerful. But is it powerful enough to survive that kind of catastrophe? The ejection is an unimaginable shock. The star gets a sudden, colossal kick. Its velocity changes in an instant. For any planets orbiting, it would be like the floor of the universe just dropped out. There are two possible outcomes, and both of them rewrite what we think about resilience. In the first, the planets hold on. Their tether to the star is strong enough that they get whipped along with it. Like passengers strapped into a car launched from a cannon. The entire planetary system, intact, is now racing through interstellar space, a flying archipelago of worlds. Their sun a lone beacon in a perpetual night, with no other stars in sight. That scenario would mean planetary systems are astonishingly robust. Their architecture can survive events of almost biblical scale. It suggests that once formed, a family of worlds is a deeply bonded unit. It can endure the galaxy's most violent storms. The second outcome is a different kind of creation. The stellar kick is too severe. The sudden acceleration breaks the gravitational bonds. The planets are left behind, like debris scattered from an exploding vessel. But they aren't destroyed. They're just set free. In that moment, a population of rogue planets is born, not from chaos within the system, but from the star's own traumatic departure. Those worlds would join the vast, dark fleet of nomads we think fill the galaxy. Their origin story written in a single, violent, stellar farewell. This extreme scenario does more than test gravity. It connects the fate of planets to the grand, dynamic environment of the galaxy itself. It suggests the story of a planetary system isn't written solely within the calm isolation of its own nebula. The broader galaxy is an active character. Close encounters with other stars or a deadly dance too near a black hole can reach in and reshape a solar system's destiny from the outside. It can compact it into a fleeing unit, or tear it apart into lonely fragments. The hypervelocity star, then, is a probe, a natural experiment. By searching for the tug of planets around these speeding suns, or by tracing rogue planets back to regions of stellar ejection, we learn about the ultimate limits of a system's cohesion. We're asking if a planetary family is a permanent bond, or a temporary arrangement, forever at the mercy of the galaxy's immense and indifferent forces. The answer is out there in the darkness, trailing behind those runaway stars. A star's final stage is demolition. A sun like ours will swell into a red giant, swallow the inner planets, then collapse down to a white dwarf. An Earth-sized ember of carbon and oxygen. Its gravity is so strong that heavy elements in its atmosphere should sink almost instantly. You'd see only hydrogen or helium on the surface. But when we look, we often see something else. Spectral lines of calcium, iron, silicon, magnesium. Those elements are there. They shouldn't be. That's the white dwarf pollution mystery. For them to be present, they have to be falling onto the star right now. An ongoing rain of debris. The source is almost certainly planetary. Asteroids, moons, maybe shattered fragments of terrestrial worlds. Torn apart by the white dwarf's fierce gravity after surviving the star's violent change. This isn't just a curious observation. It's forensic astronomy. A crime scene investigation on a stellar scale. The composition of that pollution is a direct sample. A sample of the building blocks of a distant planetary system. By analyzing the ratios of elements in the atmosphere, astronomers can deduce the bulk chemistry of the objects being devoured. They can tell if an asteroid was water-rich, or if a planetary fragment had an Earth-like core. Iron and nickel, that gives us something valuable, the recipe for an exoplanet we can no longer see. These polluted white dwarfs are tombstones and archives. They prove planetary systems can endure the apocalyptic red giant phase. Whole architectures of rocky bodies can persist in the outer reaches, only to be destabilized later, sending a shower of planetary wreckage spiraling into the dead stellar core. It's a hauntingly direct method of study. We're not inferring a planet's composition from wobbles or shadows. We are literally tasting its remains. This pollution reveals the final chapter. A solar system's quiet, relentless disintegration, where the ghosts of planets leave their elemental signatures on the face of their deceased sun. The search starts here in our own solar system, out past Neptune in the Kuiper belt. There are these icy bodies and their orbits. They tell a strange story. A few of them, their paths are clustered. They share this peculiar alignment. Their elliptical orbits are tilted in a similar way, as if something massive is shepherding them. The simplest answer is a planet. A world several times Earth's mass on a huge elliptical orbit far beyond Pluto. A hypothetical Planet 9. Its gravity would have sculpted those distant orbits over billions of years. We haven't seen it, but the gravitational signature is there. It suggests our solar system might still have a major member we haven't found, and this idea, it doesn't stop with our sun. We can look for similar clues around other stars. Take pulsars, the spinning cores of dead stars. Their pulses are like cosmic metronomes, incredibly regular. But sometimes there's a slight, rhythmic delay or an advance. It betrays the gentle tug of an orbiting planet. A hidden giant, far out, would cause a slow, long-period wobble in that timing. Around normal stars, astronomers look for the same subtle stellar wobble, but over decades. A hint that something massive is out there, on an orbit that might take 10,000 years. Or more. Finding such a world is a monumental challenge. These orbits are so wide and slow. In a human lifetime, we'd only see a tiny fraction of their path. But if they exist, they pose a direct challenge to our formation models. How do you build a gas giant so far from its star? In the standard model, the protoplanetary disk out there is incredibly thin. Sparse, material orbits slowly. Building a massive core would take longer than the disk itself likely exists. It seems an impossible place to form a planet. Yet if the evidence points to one, the models have to adapt. One possibility is these distant giants didn't form in place. They could have been scattered outward by gravitational interactions with other planets during the system's chaotic youth. A Jupiter-sized world, given a gravitational kick, could have been flung onto a vast, lonely orbit, where it now silently shapes the fates of smaller objects. Or maybe they formed closer in and were nudged outward over eons by interactions with the remaining disk gas. Their hinted existence forces a humbling admission. Our census of planets, even in nearby systems, is likely incomplete. We're excellent at finding worlds that are close to their stars, or massive, or both. But a giant on a 10,000-year orbit is virtually invisible to our current surveys. It dwells in the observational shadows. If such worlds are common, it means the outer reaches of planetary systems aren't the empty wastelands we once imagined. They may be the quiet domains of elusive titans, lonely sentinels orbiting in the deep freeze, their presence felt only through the subtle distortions they impose on the inner system. The search for these hidden giants, it's a reminder. The most profound discoveries often start not with a direct image, but with a puzzle, a slight anomaly in the data. A clustering of orbits that whispers of an unseen hand, guiding from the dark. The shadow changes shape. For some worlds that transit signal, the dip in starlight, it isn't stable. It deepens, it gets shallower, the timing shifts a little, orbit after orbit. This isn't an error, it's a signature, a planet in motion, not a static piece of clockwork, but something evolving. We're watching its story in real time. Take HAT P7b. Over years, its transit wasn't perfectly consistent. The best explanation is a precessing orbit. The planet's path isn't a fixed ellipse. It wobbles like a spinning top starting to slow. The whole orbital plane rotates gradually in space. So from where we are, the planet crosses a slightly different chord of its star each time. Sometimes it blocks more light, sometimes less. That precession is a gravitational conversation. It can be driven by the star's own shape, oblate, or by the tug of other planets we can't see. A slow dance, but we can see the steps. Then there's the atmosphere. A world like GJ 1214b, a super-Earth, showed transit depth variations that point to something else. Weather, not water clouds, but maybe colossal volcanic eruptions. Episodic, planet-wide events. They pump vast plumes, ash, and aerosols high into the stratosphere. Those hazes would change the planet's apparent size during transit, making its shadow seem deeper or more shallow as the particulates disperse or settle. We could be witnessing geology on a scale that reshapes an entire sky. A global volcanic winter, captured in the flicker of starlight. The most visually stunning possibility involves rings. Not the static bands of Saturn, but a dynamic system. A young, massive gas giant might have a vast protolunar disk, a ring system in the violent process of forming moons. Clumps of material coalesce and break apart. The ring's opacity and width change over time, casting a variable shadow. Or maybe we're seeing the aftermath of a catastrophic collision. A moon torn apart by tidal forces, its debris spreading into a new, temporary ring. A ring that will eventually coalesce or fall into the planet. The changing transit becomes a live broadcast. Lunar birth or death. These observations shatter the idea of a planet as a finished product. Static models assumed a world forms, cools, and settles into a permanent state. But these shifting shadows show us that for many exoplanets, formation is just the first act. The second act is evolution, and we have front-row seats. The forces at play: gravitational nudges, internal heat, atmospheric chemistry. They're in a constant, delicate struggle. A planet's orbit, its climate, even its appearance can be fluid, changing on timescales we can measure. This turns astronomy from a study of fossils into a study of living systems. We're no longer just mapping the architecture of solar systems. We're monitoring their vital signs, watching for the pulse of volcanism, the breath of atmospheric change, the slow, gravitational heartbeat of orbital dynamics. And in that living data, we find a universe that is not only stranger than we imagined, but more alive. The clearest pictures we have of a solar system being born, they aren't pictures of planets. They are pictures of where planets aren't. The ALMA telescope shows us young stars surrounded by these huge, flat disks of dust and gas. And inside those disks, you see these patterns. Bright rings of material with dark gaps in between. It looks like a target, a bullseye. The natural explanation is a planet forming in that gap, its gravity clearing out a path, gathering material as it goes. It's a clean story. The gap is the sign of a new world still hidden. But when you look closer, that story starts to come apart. The gaps aren't always in the right places. They can be too narrow or way too wide for the planet we think should be there. Some systems have so many gaps, more than you could ever have planets. The map of the nursery doesn't match the family that ends up living there. So if planets aren't the only thing making these rings, what is? One answer is chemistry. The snow line, that's the distance from the star where something like water turns from a gas into ice. Inside that line, it's gas. Outside, it's ice. And that change makes the dust grains stick together differently. Icy grains clump more easily. That can create a buildup of material, a pressure bump, which makes a sharp inner edge that looks just like a gap carved by gravity. It's a ring made by temperature, not by a planet. Then there's the star's own magnetic field whipping the inner disk, creating unstable zones that push dust away and leave cavities. Or photoevaporation, where the star's radiation blows the gas outward from the inside, leaving rings of debris behind. All of this paints a more complicated picture. The disk isn't just a passive sheet of stuff waiting to be carved. It's an active place. Its structure comes from heat, light, magnetism, chemistry, all of it competing with gravity. So a gap might be a planet's signature. Or it might be the ghost of a snow line, a fossilized zone where the rules for building things suddenly shifted. This disconnect is deep. It means you can't just count the dark bands in a disk and say how many planets are forming. We're learning to read a subtler language. The path from dust to planet isn't one straight road. It's a web of paths. Some lead to worlds. Others lead to dead ends or to structures that are beautiful but temporary. Our reading of these incredible images, then, is just beginning. We're seeing the blueprints. But we're only starting to understand all the architects. Planets, yes, but also these purely physical forces, all of them holding the pen. Heat doesn't just come from a star. You can get it from gravity's own pull, that's tidal heating. It can remake a world. We see a version of it here with Jupiter's moon Io. Jupiter and its other moons are in a tug of war, and that stretches Io's insides. The friction makes heat, a lot of heat. Io is the most volcanic thing we know. Its surface is always changing, covered in fire and lava. Now take that idea and make it planet-sized. Imagine a world in a stretched oval orbit. It swings in close to its star, feeling that strong pull. Then it goes far out into the cold. That back and forth isn't smooth. The planet gets stretched, then it relaxes, stretched, then relaxed, like clay. That internal friction generates heat. A tremendous amount. This isn't sunlight. It's a furnace inside the planet, burning from its orbital dance. Or think about a planet in a tight chain, like in the TRAPPIST-1 system. Even with circular orbits, the constant gravitational nudges from neighboring planets create a similar kneading inside, a steady internal warmth that changes how we see a habitable zone. The old idea is a narrow band around a star, where it's just right for liquid water on the surface, but a planet with strong tidal heating doesn't need to be there. It could be far out in the frozen dark. The internal heat from tidal forces could keep a global ocean liquid under a thick ice crust, a subsurface sea. Kept warm not by starlight, but by the gravitational pull of its star and its sibling worlds. That expands the map for life. Our own frozen moons, like Europa or Enceladus, are candidates for this. Their oceans are likely held by tidal heating from their giant planets. On an exoplanet scale, it could be more profound. A super-Earth in a resonant system might have geological activity beyond anything we know. Volcanoes, tectonic shifts, hydrothermal vents, all powered by this hidden engine. Standard models where a world is just a passively heated rock miss this. Tidal heating isn't a side note. It's a primary driver. It can thaw a frozen wasteland into a water world. It can strip away a thick atmosphere through volcanism or help replenish one. It turns a planet from a static sculpture into something living, its interior churning with energy borrowed from its motion. So when we look at a distant, icy world orbiting a dim red dwarf, we can't just call it sterile. Its cold face might hide a warm heart, a heart beating to the rhythm of gravity's song. Two stars can orbit each other at a great distance, a wide binary. Thousands of times the space between Earth and our Sun. If you were on a planet around one of those stars, the other would just be a bright point in the sky. A neighbor. Its gravity would be a faint whisper in the background. For a long time, theorists drew a line. They calculated how close a second star could get before its gravity would start to stir up the disk of dust and gas around the primary star. That stirring would create chaos. It would warp the disk or strip material away. Too close, and planet formation should be impossible, or at least severely limited. Too far, and the companion's influence fades. The question was where that line is, and what happens to planets that form right up against it. Astronomers went looking. They searched for planets in binary stars with all kinds of separations, and they found them, in places the models said should be barren. They found planets orbiting one star in a pair where the companion was close. Close enough that, according to the simulations, its gravity should have torn the planet-forming disk apart long before any worlds could form. Yet, there the planets were. Stable, this is a quiet defiance. It tells us the theoretical boundary is not an absolute wall. The protoplanetary disk isn't a fragile, static sheet. It's a dynamic structure. It can absorb external perturbations, it can adjust. Maybe the disk mass was so great it could withstand the pull. Or maybe the disk's own internal forces, its viscosity, its pressure acted to dampen the disruptive waves from the companion star, maintaining stable zones where planetesimals could still form. Each discovery of a planet in a tight binary pushes that theoretical line inward. It shows planetary formation is a stubborn process. It can persist in gravitational environments we once thought were too hostile. It thrives on the edge of chaos. Conversely, finding no planets in a very wide binary where we expected them would be just as telling. It would suggest the companion's role might not always be disruptive. In some cases, its gentle, distant gravity might actually help, by stirring the outer disk just enough to encourage collisions and growth, but not enough to cause destruction. Like a soft breeze that helps scatter seeds, these binary systems, with their vast empty spaces, are natural laboratories. They test the limits of resilience. Every planet found orbiting a star with a close stellar companion is a testament to the disk's ability to find order within a gentle storm. It suggests the cradle for planets can be sturdy, buffeted by external forces but still capable of nurturing new worlds. So the question shifts. It's no longer simply, can planets form in binary systems? We know they can. The question now is, how much gravitational interference can a young solar system endure and still build a family of worlds? The answer is written in the delicate balance of those wide, silent duos, where two suns share a galaxy, and one of them quietly builds planets against the odds. Looking at the planet sizes, there's this gap. A dip in the numbers. For planets between 1.5 and 2 times Earth's size, especially the ones close to their stars, it's called the radius valley, or the photoevaporation desert. It's a place where planets seem to be missing, and that gap tells you something. It tells you a story about what happens after a planet forms, so you have a young planet. A sub-Neptune. It starts with a rocky core, but it gets this thick atmosphere, Hydrogen and helium from the disk. It's wrapped in this big, puffy envelope. And for a while it's stable, but if it's too close to its star, a fierce, active star, then its fate is set. The star hits it with radiation, ultraviolet X-rays. That high-energy light doesn't just heat the atmosphere, it rips it apart. It gives the hydrogen atoms enough energy to escape, to leave the planet's gravity. That's photoevaporation. It's a slow boiling away of the entire sky. Over hundreds of millions of years, that process strips the world bare. The gaseous envelope gets eroded away. All that's left is the dense, rocky core. What was a sub-Neptune becomes a super-Earth. The planet crosses the valley, it changes type. So the desert in the data, it's not where planets never formed. It's a graveyard of atmospheres. It's a monument to a kind of planetary death. And that changes how you read the map of exoplanets. When you count planets by size, you're not just looking at a snapshot of creation. You're looking at a gallery of survivors and the transformed. The demographics are shaped by evolution, not just formation. The star acts as a sculptor. It uses radiation like a chisel. It carves away the fluffy, gaseous worlds from the inner system and leaves behind the durable rocky cores. It also solves a puzzle. Why are there so many hot, rocky super-Earths and so few hot sub-Neptunes? They might have all started as siblings, worlds with similar rocky cores, but different amounts of atmospheric blanket. The ones with thinner blankets had them stripped away fast. That revealed the rock underneath. The ones with immensely thick envelopes might have held on. They stayed as puffy giants, but the ones in the middle with a moderate amount of gas, they were the most vulnerable. They lost everything, and so they vanished from that part of the size chart. This desert is a reminder. A planet's story doesn't end when the disk fades. Its most defining chapter might be the long confrontation with its sun, a confrontation that can last billions of years. And it determines what the world becomes, a gassy miniature giant or a scorched, naked stone. The silence in the data, it speaks about the trials these worlds go through. The galactic core is extreme. There's a supermassive black hole at the center, Sagittarius, a star. Millions of stars orbit it, a dense and frenetic swarm. The radiation is intense. X-rays, gamma rays, they flood the space. Stellar collisions happen, close encounters. They're not rare, they're part of the environment. It's the last place you'd look for a peaceful nursery, for new worlds. Every standard model says the disks around young stars there should be torn apart. Blasted by radiation, shredded by gravitational tides from passing stars, or swallowed by the black hole's pull. That chaos should prevent it. The gentle accumulation of dust into planets. It should be a dead zone, but the clues say otherwise. Microlensing surveys, they detect planets by how their gravity bends light. They've suggested a population of worlds. Not in the quiet suburbs, in the bulge, the crowded, violent heart of the galaxy. If confirmed, these are the ultimate survivors, planets in the most hostile environment imaginable. Their possibility forces two ideas. First, that planet formation isn't delicate. It doesn't need a quiet workshop. It's phenomenally robust, a stubborn, fundamental force. Wherever there's dust and gas orbiting a star, no matter the neighborhood, gravity will try to build something. The process might be accelerated, compressed by the pressure. Disks might be smaller, lifetimes shorter, but in that frantic rush, planets could still coalesce. The second idea is more dramatic. Migration on a galactic scale. Maybe these worlds didn't form in the inferno. They were born in quieter outer regions, and then, over eons, their star was drawn inward, toward the brilliant, deadly core. The planet, holding on, was carried along, a passenger on a doomed voyage. It now endures conditions that should strip its atmosphere, sterilize its surface. A captive in a cosmic prison. What would that world be like? Its sky would never be dark. It would blaze with the light of millions of nearby stars. Its surface, bathed in constant, mutagenic radiation. The concept of a habitable zone seems almost laughable. And yet, The discovery would teach us about tenacity. It would mean the building blocks of solar systems can exist even in the realm of monsters. They can persist in the glare of the core, orbiting stars dancing on the edge of annihilation. Finding them would be the final proof. Planets aren't a privilege of calm, safe places. They are a universal phenomenon, a testament to gravity's quiet, persistent work. Even in the loudest and most violent corners, the final frontier isn't out in space. It's a limit in how we see. We've built this whole catalog of strange planets from what our tools can pick up: the big gravitational pulls, the clear shadows against a star. And that's given us a gallery, a spectacular one, but it's skewed. We see the giants. We see the ones that orbit close to their suns, the ones that pass right in front from our line of sight. But the rest, the quiet ones, the distant ones, the small ones, the ones whose orbits never cross our view, are models for how planets form. They are prisoners of that. They're built to explain the strange things we can see. And we have to admit, the universe's real creativity is probably in the things we can't see yet. Take an Earth twin, a world with oceans, continents, orbiting a sun-like star at just the right distance. We haven't found one, not because it's rare. Because its signal is a whisper. The wobble it gives its star is tiny. The shadow it casts is almost nothing. Our telescopes right now are straining at the very edge to catch something that subtle. So our ideas about habitable worlds, their extrapolations. From the loud planets, the large ones, the extreme ones. We don't have the data yet to know if our own solar system is a fluke, or a common blueprint, or the free-floating Earths, rogue planets our size drifting in the dark. Models say there could be billions of them, more than stars. But how do you find a cold, dark rock floating alone? Microlensing gives us glimpses. A star brightens for a moment as the planet's gravity bends its light. But it's a single event. You can't study that world again. Its composition, its history, its potential, it's all locked away. Our understanding of how it forms, whether it was ejected or just collapsed alone, that's all theory. Not observation, and compositions, things we haven't imagined, carbon worlds, diamond planets, worlds of molten metal or exotic ice. To confirm that, you need to study atmospheres. Surfaces, and right now, that's only possible for a handful of planets. The largest ones, the hottest ones. For every other world, its true nature is a guess. Our models of planetary chemistry, they are based on a limited palette. The elements we see in our own solar system, the atmospheres we can currently probe. The cosmos has a much broader periodic table to work with. Combinations we haven't dreamed of. That's why the next observatories matter. The Nancy Grace Roman Space Telescope, with its wide-field surveys, it'll find thousands more planets through microlensing. It'll look toward the galactic bulge and finally give us a census of those lonely rogue worlds. The extremely large telescope, with a mirror nearly the size of a football field, it'll have the power to directly image smaller, cooler planets in nearby systems. It might even analyze light from an Earth-like atmosphere. Look for water, for other molecules, but with every new window we open, we have to be ready. The view might shatter our expectations again. These 30-odd bizarre systems we've found, they're not the conclusion. They're the prologue. They're the loud, obvious anomalies that made us question our first, simple ideas. The biggest challenge to our models isn't the hot Jupiters we've already catalogued, or the super puffs. It's the silent architectures waiting in the dark. Systems with orbits tilted in 3 dimensions. Planets made of materials we can't name. Earth twins in places we thought were barren. The future isn't just about finding more planets. It's about discovering the kinds of planets our current models can't even predict. Models built on biased data. The final mystery, maybe the most profound one, is that we still don't know what we don't know. The grand narrative of cosmic history is being rewritten. Each of these 30 systems, with its own impossible story, is a piece of a much larger puzzle. And that puzzle shows planetary formation isn't a single, tidy process. It's a diverse set of pathways, a spectrum of possibilities. It's filled with chaos and migration and destruction, and a kind of quiet resilience. The standard models, core accretion and disk instability, they're not wrong. They're just incomplete. They represent a subset of possibilities, a few chapters in a much richer, more complex book. The existence of hot Jupiters, rogue planets, diamond worlds, it means our solar system's calm. Orderly architecture might be the unusual one, the quiet street in a universe full of cosmic traffic. This isn't a small revision. It's a fundamental shift in perspective, a revolution in how we understand our place. And this revolution has a direct impact on the most profound question, the search for life. If the pathways to building planets are this varied, then the range of possible habitable environments expands, far beyond our old, narrow definitions. We're no longer looking just for a second Earth, a twin of our own blue marble orbiting a sun-like star. The search now includes tidal heated moons, orbiting gas giants in frozen outer systems, kept warm by gravitational friction. It includes the thin, temperate bands of eyeball planets, staring out from the dark side of a red dwarf. It even includes the ancient, quiet neighborhoods around white dwarfs, where a surviving world might orbit a cooling stellar ember. Long after its sun's violent death, each bizarre system we've catalogued is a lesson in cosmic diversity. It teaches us that life, if it exists, won't be found only in places that look like home. It could be thriving in environments we once considered hellscapes, or in profound isolation, or in the ruins of a star's final act. This grand synthesis is humbling. It tells us the universe is more creative, more violent, and more patient than we ever conceived. Our models are maps, but the territory is vast and wild. The next time you look up at the night sky, consider not just the points of light, but the silent, dark spaces between them. For in those spaces, the true story is being written. In the gravity of unseen giants, the slow drift of orphaned worlds, and the quiet, persistent chemistry on a million different kinds of ground, we've gone through 30 systems that don't fit the old patterns. And you don't end up with one answer. You end up seeing things differently. The neat models we had, they aren't thrown out. They're just part of something bigger. And messier. Core accretion, disk instability, those are real, but they're not the whole story. They're like a steady beat. And over that, the universe is improvising. With gravitational encounters, stellar winds, just chance. Each strange planet we find, it's a fossil of that improvisation. A hot Jupiter marks a migration. A retrograde orbit is a scar from a gravitational slingshot. A super puff might be a world evaporating. These aren't mistakes, they're clues. In the biggest detective story there is, how worlds are made. And it forces a kind of humility. For a long time we thought our solar system was standard, maybe common. Now it looks like it might be a quiet street. In a city full of cosmic traffic. Our stable orbits, our giant planets far out, our single star. That might be the exception, not the rule. Earth isn't the template. It's one example. In a huge menagerie of possibilities, that shift, that's what drives science. A model that isn't challenged is a story you never hear. These 30 defiant systems, they push understanding forward. They make us build better telescopes, write more detailed simulations, ask new questions. And as the technology gets better, we'll see deeper. We'll find architectures that make today's oddballs seem normal. We'll map atmospheres of distant Earths. Taste the chemistry of alien oceans. This is just the start. So next time you're under a clear night sky, look up, remember, out there are worlds that orbit backwards. Worlds that could float on water, worlds made of diamond, worlds with no sun. Each one has a story, written in gravity and heat and time.